Hi, welcome to Lab 7 titled Buffers. Before we get started, let me introduce myself. My name is Professor Coburn, and I teach one of the Chem 110 labs. I also teach other courses at CI, so I might see you further on in your career as you move forward here. In Lab 6 and in your lectures, you have been studying acids and bases. An acid is a solution that donates a proton or a hydrogen ion in solution. A base is one that accepts a proton or a hydrogen ion in solution. In today's lab, we're going to build on what you've been talking about in lecture and in Lab 6 and talk about pH and buffers. The goals of Lab 7 are to learn about measuring pH and to explore the properties of buffer systems. Why is this important? Well, your body contains a very, very powerful buffer system, and that's in your blood. In your blood, you have a weak acid, carbonic acid, and its conjugate base, a bicarbonate anion. And these two work to regulate the pH within your body. If this breaks down, it can lead to serious effects on your overall body, including death. So again, your body is an amazing buffering system. So to understand that, we're going to explore some of the characteristics of buffers in this lab. This lab is composed of 3 parts. The first part is this introduction, which is what I have started here. I'm going to move it into a PowerPoint and give you background on both pH and buffers. It might be repetitious a little bit with your lecture. I might teach it a little differently, but hopefully it will help increase your breadth of understanding. You'll then watch a video on measuring buffers and answering a set of questions in your worksheets. Finally, you will be watching a simulation lab. In the simulation lab, you'll see a titration similar to Lab 6, but this time it's with a weak acid, acetic acid, and its conjugate base. We will use this simulation lab to further our understanding of an important buffer equation, and that's the Henderson-Hasselbalch equation. We'll also be using this simulation to understand various parts of a buffer titration curve. With that said, I'm going to be moving over to a PowerPoint presentation to further provide background for this lab. Again, welcome to Lab 7 titled Buffers. An important measurement of a solution that reflects the chemical conditions is the amount of hydrogen ions. We talked about that a little bit earlier with respect to acids and bases. The measurement scale that we use to define the amount of hydrogen ions in solution is pH. And this is a logarithmic scale. It's based on factors of 10. The pH of a solution is defined as the negative log of the hydrogen ions in solution. So pH is equal to negative log of the hydrogen ions, or the concentration of the hydrogen ions. If we have a large number of hydrogen ions, then our negative log is going to be small. If we have a small number of hydrogen ions, our negative log is going to be big. And how do we compare this, and how can we kind of figure this out within there? And we tend to talk about a neutral pH being water. So if water is a neutral pH, if a solution has a pH less than water, then we call it an acid. If it has a pH greater than water, we call it a base. And our pH of water is 7. So pure water has a hydrogen ion concentration of 1 times 10 to the negative 7. So when we have acids, or acids are compared to pure water, So any solution with a pH less than water is an acid, and any solution with a pH greater than water we call a base. Some common acids that we know about: lemon juice, very strong acid. Our coffee is acidic, and even milk is slightly acidic. So we go from more acidic to less acidic as we get closer to water. If we go on the base side of water, so anything with a pH greater than 7, we're looking at hand soap, we're looking at bleaches, even eggs are what we call slightly basic. The other important thing we should talk about is the measure of hydroxide ions. So pH is the measure of hydrogen ions. Well, the measure of hydroxide ions is called the pOH. And it is comparable to the pH in the sense that it is the negative log of the hydroxide ions in solution. And so when we look at the relationship between pH and pOH in solution, if we measure the pH of solution, the pOH is always going to be 14 minus the pH. Or the pH plus the pOH is always going to be equal to 14. We said that water is neutral. Well, we said water has a pH of 7. For this relationship to be true, and this relationship will always be true, the pOH is also going to be equal to 7. Now you can start to understand why we say that pure water is neutral. The pH equals the pOH, or they're both equal to 7. So our relationship, important relationship between pH and pOH here, that same relationship holds if we look at it with respect to the actual hydrogen ion and hydroxide ion in solutions. So in this case, if you multiply the hydrogen ion concentration times the hydroxide ion concentration in solution, it will always be equal to 10 to the negative 14th. For me, it's easier to always talk in terms of pH and pOH because my numbers are smaller, or in this case they're larger, but they're whole number that we can more easily talk about. So again, we've talked about the relationship of pH and the hydrogen ion concentration, where the pH is equal to negative log of the hydrogen ion concentration. We've talked about the relationship of our hydroxide ion in solution versus our pOH. Again, our pOH is negative log of our hydroxide ion. And we've talked about the relationship between the pH and the pOH. The pH plus the pOH is equal to 14. We have two main ways that we measure pH. And you've probably heard of both of them. One is the litmus paper. And litmus paper works in such a way that there's an indicator. The paper has an indicator on it. When we put that paper in solution, it will change color depending on the indicator color that's in there. And I won't go into the chemistry behind this, just to have you understand that when we measure with litmus paper, the paper has defined indicators on it. Depending on the precision that we want in there, we get different papers for it. And the indicator will change color. And that color change we can equate to the pH of our solution. And we will be also using an indicator in the simulation lab. You'll see it change color. That indicator is very similar to what we have on litmus paper. The second way that we measure pH is with a pH probe. And let's go a little bit into a pH probe and how that works. So pH probe works by measuring a voltage difference between two electrodes. So you've probably seen a pH meter, or you will see it in the video coming up. And there's a probe that we put into solution. That probe actually has two voltages, and we are comparing the difference between those two voltages. We put our pH meter into two dramatically different pHs, and we call this calibration. And you'll see that also being done. We'll put it in a pH of 4 and a pH of 10. And when we calibrate that, what we're telling the instrument is that if you have a voltage difference of this, A, that means it's pH of 4. If we have a difference of this, which would be larger, we have a pH of 10. It then puts a regression between the two and says that any difference between here, voltage difference that you measure between here, is going to be relative to what we have put as the two voltage differences of our calibration. So that's how a pH meter works in kind of simplified form. But understand that you're measuring a voltage difference, and your calibration is what defines how it knows what voltage difference it is to be able to compare it to a pH. Interesting, it also has a temperature probe in it. We measure pH can vary based on temperature, so understanding what the temperature is when you're measuring a certain pH also becomes important. So when we said that water is our neutral standard, we say it's pure water at 25 degrees C. So let's move into buffers and what a buffer is. A buffer is a mixture of a weak acid and its conjugate base, or a weak base and its conjugate acid, one of the two. It is unique in the sense that it will resist changes in pH over a range of adding a strong acid or a strong base. So this is what we call the buffering region. As you can see here, we're adding a strong base, and that's sodium hydroxide. And over the distance, and here we're over 20 milliliters that we're adding, you can see that our pH resists change. And that's what we define or a buffering characteristic. It does require a weak acid and its conjugate base, or a weak base and its conjugate acid. And what's going on in this buffering region is that there is an acid-base equilibrium going on. So since it's weak in its acidic or basic characteristics, if you add a strong base to a weak acid, it's going to drive equilibrium or stay in a state of equilibrium. Shifts it over one way or another way, but it maintains that equilibrium. There's a point where it loses what we call its buffering characteristics, and this is what you see happening here. And I'll get a little bit more into a titration curve as we go further into this presentation. When we measure a buffer, we measure it based on its equilibrium constant. So again, what I said with a weak acid and its conjugate base, or weak base and its conjugate acid, they have a state of equilibrium going on. And when we measure the equilibrium constant, and again, equilibrium constant is a ratio of the forward direction versus the reverse direction of any chemical reaction going on. When we measure this ratio in a buffering system, we call it the Ka. It's the equilibrium constant, in this case, of an acid. So if it's a weak acid and its conjugate base, we call it Ka. If it were a weak base and its conjugate acid, we would call it the Kb. We can take the negative log of this, very much the same as we did the pH or the pOH. We call it the pKa. If we were to do the same thing with the conjugate base, weak acid side of it, we would call it the pKb. The relationship between the pKa and the pKb in any solution is the same as the pH and the pOH. The pKa plus the pKb is equal to 14. So again, the pKa is the negative log of the Ka being the equilibrium constant of a weak acid and its conjugate base. The pKb is equal to the negative log of the Kb, where Kb is the equilibrium constant of a weak base and its conjugate acid. And when we add these two together, again, this would be the weak acid and its conjugate base, or the weak base and its conjugate acid. When we add those two together, they equal to 14. The relationship of the Ka and Kb is the Ka times the Kb is equal to 10 to the negative 14. So very important when measuring buffers is understanding the equilibrium constant and the Ka or Kb of a solution. We have tables with this. In this case, we're measuring the Kas. This is a weak acid measurement with it. One important one you'll be using in the titration that we do today or in the simulation lab, we're working with acetic acid. It has a Ka of 1.8 times 10 to the negative fifth, and its pKa is 4.74. So what do we know about Ka and Kb and their magnitude? So if Ka is large, then we know that the K1 is going to be significantly greater than the K negative 1. Or it's going to be skewing the reaction to this side. If the Ka is small, then reaction is going to be more skewed to the weak acid side of it. So high Ka, the reaction is skewed to the weak base side of it. A low Ka, it's skewed more towards the weak acid side of it. Oops, going the wrong way. So the relationship, now let's talk about the relationship between pH and pKa. And the definition of this relationship is what we call the Henderson-Hasselbalch. And you probably had this in lecture already. But the Henderson-Hasselbalch does define the relationship between the pH and the pKa. So what the Henderson-Hasselbalch says is that the pH is equal to the pKa plus the log of the ratio between a conjugate base and its weak acid. So the pH is equal to pKa plus the log of the ratio between a weak acid and its conjugate base. Very, very powerful equation. If we look at this equation, and this only works when we talk about buffers within this buffering region. Outside of this buffering region, when we hit this point here, then that Henderson-Hasselbalch equation no longer applies. Now let's look at a titration curve between a weak acid and its conjugate base. And what we're going to do is we're going to take a weak acid and titrate it with a strong base. What we see here is what we've talked about is this buffering zone, where over a period or a amount, quite a large amount of milliliters of strong base, we see very little change in the pH. it hits a point where all of a sudden we see this dramatic change in pH. We call this pivot point where it goes dramatically in this case, to a basic form, the equivalent point. And what's going on here chemically is that we've maintained an equilibrium between a weak acid and its conjugate base. But you can only add so much strong base in before we've used up all that weak acid. The equivalence point is where there's no more acid or no more hydrogen ions in solution to be able to react with our sodium hydroxide or our strong base in this point. So since there's no longer any hydrogen ions or weak acid to be used, you only have base. And this equivalent point now shows that you've gone completely basic. So you're pretty much up at this point just measuring your pH of your sodium hydroxide. So that's the equivalent point, and it's the point where you've used up all of the hydrogen ions that are coming from your weak acid. We have a point that we call the half equivalence point, and if you measure it, this is 50 milliliters, your half equivalence point would be exactly half the milliliters required for that. In this case, it's 25. This half equivalence point is an important point. At this point, your ratio between your weak acid and its conjugate base, this ratio is equal to 1. So you have equal amount of your weak acid and its conjugate base. So when that relationship is equal to, that ratio is equal to 1, your log is equal to 0, and your pH is equal to your pKa. So if you look at a titration curve with a buffer, your half equivalent point, or the point exactly midway between your starting point and your equivalent point, as far as volume, in this case of base that I've added, is where your pH is equal to your pKa relationship of your, and that's, you can see it with the Henderson-Hasselbalch, and you can also define it by creating your titration curve, understanding your equivalent point, and then going halfway back from that. So that's a little bit of background. Let me kind of refresh you with what you'll be doing with the rest of this lab. So after this, you'll watch a video to further understand pH and in doing pH calculations. You will then follow a simulation lab. Unfortunately, I'd love for you to have been able to do this simulation lab. And in this simulation lab, what you'll see me doing is preparing a buffer. And then as I prepare the buffer, I will have you stop at certain points to record findings in your worksheet. You'll be working through the Henderson-Hasselbalch equation, and then you will be taking the data from this titration to create buffer titration curves. So hope you have fun with it. I enjoyed setting up this lab, and if you have any questions, make sure you ask Professor Burnside or your Chem 110 lab instructors. Take care. Have a good one.